Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So if an element is just like some number of protons and neutrons and electrons, if you just add more of those things, like, could you just get infinite elements forever? Like, if you have a million protons and neutrons and electrons and you add one more, like, would that be a new thing just forever?
Darn it, Lions. I'm a chemist, not a particle physicist, but with my very limited level of expertise and very limited knowledge set, I will attempt to opine to this. And what you just basically gave was a scientific equivalent of, can you just have a mint? But it is wafer thin. Like, can't you just keep adding more food to the human body? It's like, no, but what if it was just a mint? What if it was wafer thin? So bottom line up front, maybe, and probably not.
That's a sciencey answer.
Yeah, that's like all of science basically, which is can A, maybe, probably not. Anyway, so interestingly, when I was double checking and researching this one, is I almost didn't try to answer the question because I'm like, there's so much theory here that I was like, I don't know if this would be interesting to listen to. But then I was like, no. I managed to find some stuff that I was like, okay, I feel that this is, I can split this up in a way that kind of makes sense. So let's start at the very beginning, which, if I remember from The Sound of Music, is a very good place to start. What, as you kind of mentioned, right? You've got the three main parts of an atom: protons, neutrons, and electrons. Where are all of those located?
That feels like such a high school chemistry teacher way to phrase that.
Well, I don't know if you're going with the plum pudding model where it's all just kind of.
So the way it was taught when we were lads, and I think for most of the several generations before, is the proton and the neutron form the nucleus, and the electron orbits in a perfect crystalline orbit around it. But the way I remember it kind of morphing as I got older, college and post-college ages, the protons and neutrons are in the nucleus, that's still true, and electrons are just kind of a background radiation we have a hard time objectively measuring, but orbits are handy.
Yes. The protons and neutrons are in the center, and then the electrons are like a high librarian where he's like, I have no idea where those books meant. Wait, there's a lot of them about, So and interestingly, I do think that it is still taught that way because it's a convenience lie, right? When you're first teaching it, right?
Spherical cows.
Yeah. It's like, and then there's electrons around the outside. It's like, okay, cool, I got this. And then later on, you're like, it's really more of an electron cloud, which is and when you see it, the dispersion of it, it's like, this is where there is a higher and lower probability of finding an electron should you go looking. Because quantum physics is a thing. So there's two main things. There's two main possible limitations on whether or not there could be infinite elements. One deals with the size of the atom, and I think that this is, according to particle physicists, the less likely thing to limit it. There's actually another thing that is more concretely where they're like, this is probably it. So I'll talk about the more theoretical one first, which is that so atoms have different sizes, which I think is kind of neat. And so if you picture a periodic table, right, as you go to the right and up, atoms get smaller. As you go down and to the left, they get bigger, right? And the reason why I think is kind of interesting. So imagine you're in a row of the periodic table, right? So let's say you're starting with lithium, right? Lithium has all of these electrons because 99% of the volume of an atom is the electron cloud, right? 0.1% of its, I think 0.01 or something like that. A very, very small volume is the actual nucleus. A lot of times it can be just considered to be a point, know? Yeah, it is the analogy I was given was if you took a football field and you placed a marble in the center of it, that is the ratio.
In volume.
Yes.
But not in mass.
99.9% of the mass is in the nucleus.
Right. Okay. I was going to say, I need to make sure I heard him correctly, because otherwise everything I thought I knew is wrong. But no, we're on the same page. Carry on.
Yeah. All like basically it's like you got a steel ball bearing in like a room full of flan, like it's like all of the mass and none of the volume, So as you go to the right, you're adding more electrons, but you're not adding more energy levels, right? So as you drop down in levels in the periodic table, you add new energy levels, which makes the thing way bigger, right? So as you're just adding protons, right? Those protons actually pull on the electrons harder. So it actually kind of like makes it tighter and tighter and tighter until you drop to the next level and goes, new energy level. And then like it gets way bigger, right? So for an example, lithium has an atomic radius of 152 picometers. Fluorine, on the other hand, is 42 picometers, right? So it gets way smaller. But then when you just drop to like, so that's fluorine. If you add two more atoms, because I didn't do the noble gases because they're unreactive and I don't like them. But if you add two more protons, right, to fluorine, it all of a sudden balloons up to 227 picometers. Right? Yeah. So it gets bigger. And then it shrinks back down to 172 and then back up to 280. And it shrinks back down, right? So it always getting bigger, but like it condenses, right? So I say all of that to say that one possible limitation is that as the atom gets bigger, and as we have said that most of that volume is made by the electrons, right? The electrons have to move faster, right? Because they effectively have like more distance to cover in order to hit all of their probability areas. And eventually, as t goes to infinity, right, as when we add the millionth proton, right, the electrons would have to move faster than the speed of light in order to cover the distance that they would need to in that particular valence shell. So I think it was Feynman predicted that it would be at element 136, but others predicted it would be at like 170, but I think we're at 118 right now, so that's still a lot, you know?
Yeah, you've got all kinds of space.
There's tons of elements, right? But then, so that's one, is it's like, oh, well, eventually the electrons just can't move fast enough to cover this like massive space, which is like, okay, neat.
That is kind of like a fun way for it to not work, because it's like at those scales, like the speed of light isn't fast enough. And anytime the speed of light isn't fast enough, it's like, oh.
Yeah. Well, and that's the thing is I feel like that Star Trek and video games spoiled me, because I'm like, I want to explore the universe. It's like, yeah, the speed of light isn't fast enough. And it's like, but I wanna. And
no.
and but it'd be cool though.
Too bad. The spice must not flow.
But one of the other things that this actually, doing some research on this, I was like, it helped refresh some stuff in my mind, because I was like, it's one of those things where I was like, man, this kind of doesn't make sense, right? Which is, as you mentioned before, all the protons are in the center, right? With the neutrons, right? So riddle me this, Batman. If you put a positive magnet next to a positive magnet, what happens?
They repel each other.
Yeah. So why does that not happen in the nucleus? Because you only have positive and neutral charges.
Neutral.
It's magic.
Is it magic? I think it
is magic.
I think it is magic.
Show over.
Yeah. I'm gonna guess there's some very magic balancing between the electron cloud, which is negatively charged, and the protons, which are positively charged. Like they do some sort of balancing act. This is me speculating wildly.
No, yeah. I love this. Yeah. I love this because it's like they do some type of a fusion dance. And, we started with magic, so anything I say from there is by definition be more scientific. Yeah. But I mean, if you think about it though, right? So like the electrons are circling around on the outside, right? So if anything, they would be making the situation worse.
It's got to be gravity. Gravity.
Yeah, you're actually closer with gravity, weirdly. So this is where we get into cool, interesting physics stuff. So do you know what the 4 fundamental forces are of the universe?
I think I know what you mean, and I think they have like stupid names to mess with kids in school. Isn't it
You're
like
thinking of quarks, and there are like up, down, strange.
Strong, yeah, strange. Isn't it like there's like strong, weak? Are those the forces?
Those are two forces. Yeah.
Yeah. Okay. So there's like, I think I am thinking half of forces and half of quarks.
Half quarks.
Yeah. So I'm going to say strong, weak, strange, and Jamiroquai.
Sweet. Yeah. No, you cast a wide net there.
Yeah.
No, as we all know, the four fundamental forces are earth, water, fire, and air. And
damn it, I did know that. And the four humors.
And as we all know, they can all only be wielded by one person, but each person can wield one,
except for the Avatar.
Yeah. No, you're actually close. So it's
I was close with Jamiroquai.
Yeah. So it's the strong force, the strong nuclear force, weak nuclear force, electromagnetic force, and gravity. Yeah. So gravity is interesting because gravity is, I believe, the weakest of the four, but it works over technically infinite range.
Imagine being weaker than a force called the weak force.
I know.
How do you not feel bad about that?
Gravity's marketing specialist really needs to get on the ball.
Yeah, come on.
They're like Gravity's sitting there, like looking at like all of the other strong forces names, like coming across like the ticker, and somebody says like the weak force, and then like their marketing person just throws all of the papers up in the air, and it's like, nope, that's it, we're sunk. No, one of the things I think is interesting about gravity is that the gravity's impact on you is based off of, if I remember correctly, the mass of the two objects and then the distance between them. But if you look at the equation, right, is that it never goes to zero. It just gets smaller. So technically, a planet on the other side of the known universe is pulling on me a little bit, just not an appreciable amount, right?
And you are pulling on it.
Yeah, exactly.
Yeah.
Yep, absolutely. Which actually reminds me of the one time when I realized that knowledge and tact were two different things, because my stepfather, I had learned that gravity was, like due to mass and distance, right? And I said, oh yeah, so cool. So like I have gravity and I technically pull on the things around me. And my stepfather said, no, that's not true. And I'm like, no, it is. I just learned it. Isn't it neat? Because I was like in 8th grade. And he goes, no, that's not true. And I said, well, then what gives the planet gravity? He goes, the fact that it's spinning. And then I started spinning in place, saying out loud, do I have gravity now? Do I have gravity now? Do I have gravity now? And I got grounded. And so it didn't matter that I was right. It mattered that that was not the time to prove that point. So, still learning. Anyways, so that's gravity. The weak nuclear force deals with like nuclear decay and stuff. So I don't know much about it. The main one that we use in chemistry is electromagnetic force, which is when we talk about, like electrons and protons would be attracted to each other, right? Negatives and negatives repel, all that sort of stuff, right? The strong nuclear force is incredibly strong over very short ranges. And one of the things that I think is really interesting about the strong nuclear force is that it's actually not only does it hold the nucleus together, but it actually is what holds elementary particles like protons, or sorry, not elementary particles, atomic particles like protons together. So there's a reason why you never find quarks like about. And the reason why is because if the strong force actually gets stronger the further away you pull things, right? So if you start to pull on the two quarks of an electron or of a proton, you will actually generate enough energy from them trying to pull themselves back together that they will generate enough energy to generate new quarks, and then what's called encapsulation, where they will just make new protons and neutrons. And I love that about physics, because physics is like, I don't want you looking at the quarks, and we're like, we're going to look at the quarks. It's like, no, you know what? I'm going to make new matter, because screw you, man. I said no.
Don't come in here. Don't come in here.
But the strong nuclear force is at the subatomic level enough to overpower electromagnetic force, right? So the protons are repelling each other, and that's why neutrons need to be there to act as a degree of a buffer. But the strong nuclear force keeps it all knit together. But as you start to make the nucleus bigger and bigger and bigger, electromagnetic forces start to play a more predominant role in that interaction and overpower the strong nuclear force, which is why a lot of the heavier elements immediately fly apart, right? So, because, it's the protons are far enough away from each other that the electromagnetic force is the predominant force, not the strong nuclear force.
So I just want you to know that this is actually bookending something that you have been doing the whole time I've known you, which is when you are sciencing about some fun science thing and you talk about like super heavy elements flying apart, there was always that part of me that was just like, what I mean, like, I kind of understand what he means, but like, what exactly does he mean? And now I know.
Yeah, you just gotta push apart. So there is some theory about there being like islands of stability where it's like you can have the exact right proton and neutron configuration such that like the way they all sit on each other, that they're arranged in such a way that like they don't repel each other enough and the strong force is able to keep it knit together. We have yet to find that. But to your point, if you added 1 million, the protons on the very end are in no way going to be attracted by the strong nuclear force and they would fly apart. So there may be some items of stability, but as far as could there be infinite? No.
Sad. I
know, right?
I like to think of the universe as like, this is an infinite place. Like we could do all kinds of, and then I have to remember that like mathematically, like infinity is a complex concept and like there are limited infinities and like subset infinities. And this is just one of those things. We can't have infinite elements.
Infinity is one of those things that there is no part of evolution that has prepared our mind for it, right? Because I remember saying to one person at one point is I said, you know, well, if you go with like multiverse theory and there's theoretically an infinite number of universes, then thing A is possible. And they were like, oh, well, yeah, but like, isn't there a very, like, an extremely small chance, like a 1 in a bajillion chance of thing A happening? I'm like, true. But 1 bajillion, 0.00001 times infinity, still infinity. So technically, if there's any chance of happening, it has happened an infinite number of times, which is messed up. The only time when it didn't happen is if it happens never. It either happens never or always and everywhere. You know, and it's like that doesn't make any sense to us, you know? Yeah. And to be fair, the universe itself may be infinite. It's just that the number of blocks that you've been given in Minecraft to play with are finite.
Yeah, I'll take that because you only have so much inventory space. Which actually reminds me of another thing I would ask you about.